Well, good morning and welcome. I hope you all managed to get in without too many difficulties. I gather there were some stale links. It's good to have you here. It is a bit strange being this side of a screen and having you all sitting all over the world, I guess, watching this presentation. But I'm glad for the tech that makes it possible. I'm going to be looking, as you can see, at Lambdas and taking a kind of view right the way through from the beginning to the modern C++. Looking at what this syntax means, wondering where we might use it and why, and in particular, what other ways there are of doing the same things. So to start with, what's the problem to which Lambdas may be a solution? And the thing is, there are times when we want to pass around effectively little bits of code with hopefully minimal syntax. And Lambdas are a way in C++ of providing a relatively terse way of doing that. So one of the typical use cases is you're invoking perhaps a standard library algorithm. And one of the things it takes is some sort of predicate. Now, you could write a fully fledged separate freestanding predicate, or you might want to provide just a small piece of code that the function you're calling, algorithm you're calling, can use. The concepts are not the concept of a lambda is not specific to C++. Many of you, I'm sure, use other languages where they have lambdas. The syntax varies from language to language, and of course, because it's C++, there are some issues that are specific to the complexity that we have in the C++ language. Now, Lambdas have been in C++ for 10 years, but that's only just over a quarter, really, of the life of C++. So I thought I'd start by looking back at what we did before we had Lambdas available. It's quite useful, I think, sometimes to do this, to see what the context was. It can explain some of the things that seem odd when you look at Lambdas from the outside, or other features in C++ as well. And also, of course, because of the way C++ has developed and continued, very, very few things are deprecated. So as we'll see, the techniques that we used to use are still available. And it's not necessarily the case that you want to use Lambdas in all the places where they can be used. So let's start with a C++ 98 use of algorithms. One of the things that really was new and novel and interesting and quite revolutionary when C++ 98 came out was the STL, the Standard Template Library. And it was based around this concept, as I'm sure most of you know, of iterators and algorithms. And you could pass iterators from a range of different collection types into standard algorithms and mix and match between iterators and algorithms. And many of the algorithms came with additional predicates, which could be defaulted. And the idea was to provide you with a building block. The intent was that although the standard provided a few containers, they weren't the only ones. And although the standard provided a few algorithms, again, they weren't the only ones. And at its best, the use of the STL enabled you to write some very terse code that was really powerful. So a trivial example on the screen here, we've got some sort of function that takes a vector of int by reference, and we want to sort it. And as part of the algorithm, the ... dots are code I'm not showing. So we just call std_sort with v.begin and v.end. And this code probably looks fairly familiar, I hope, to anyone who's used C++ in the last 20 years or so. But it's hiding quite a lot of things going on under the covers. So first off, we're instantiating a specific specialization of the sort template that's provided in the standard header. And we're going to provide an instantiation that is specifically targeting the types that we provided, v.begin and v.end. So it's as if we wrote std_sort with std_vector int iterator as the instantiating type. But of course, you'd almost never write that because you rely upon the template argument deduction populating the arguments for the template that we're calling. But that is happening under the scenes. So if you call std_sort somewhere else with a vector of different types, or a different collection class completely, you're instantiating a completely separate specialization of the sort algorithm. So this means that inside the instantiation of the algorithm, it's type safe. The right comparison operator will be used based on the types of the arguments you provide. It also means that because the compiler is effectively stamping out the function for you that's specifically designed to do vector of int, it's going to be faster, typically, than using functions like C's qsort. And one of the sort of party tricks that people were using in the early days to try and persuade people that although it's doing lots of clever things at compile time, runtime can be very efficient, was to demonstrate that you could sort a vector of ints or other things with std sort faster than you can, in many cases, with qsort. Now, this was just the beginning, of course. You may want to sort in a different way. So what happens if you want to sort in reverse? Well, some customization was quite easy. There were various other modifiers and things you could use, function objects of various sorts that you could use to do this for you. So here's a simple example where we add a third argument on the end of sort, std greater int, and it uses that rather than the default of std less. It's pretty clear when you read the code what it's doing, and it's hard to get wrong. Well, maybe not. It's easy to get wrong syntactically. It's hard to get wrong logically. Syntactically, there are various things you can do. You might miss out the things at the end. Why do I need to provide the left less than int greater than and then the parentheses? That doesn't seem strange. It seems strange. I might forget that. That's an error. I might miss out the final parentheses. That's an error. I might miss out the int. That was an error. In C++17, that became valid. We might accidentally put the wrong type in. That's possibly a more serious problem. We instantiate std greater with bool in this example. That's going to go badly. We're going to sort beginning and end a range of ints, and we're going to compare them by using the bool version of std greater. That's going to check whether or not they're 0, which is probably not what we wanted. But the principle was that it was reasonably straightforward to compose things as long as these building blocks like std greater were available. And in C++14, we did add something to make it simpler to do the use of things like std greater by just taking out the type. And there was a specialization for void that just did the right thing. And C++17 made it simpler still because class template argument deduction meant you could actually miss out the template bit completely and just go std greater. And the compiler would deduce the type based on the arguments from begin and end and what was required by std sort. So it's getting simpler, but it's still not perhaps quite as simple as you want. And in particular, if you want to do something for which there isn't an existing function object. So let's take a very simple example. We want to change our algorithm to sort not just values, but the absolute value. What do we put between those slash star star slash? We need to provide some sort of functoid, function or function object that will compare the absolute value of things in this vector, things between beginning and end. Now, there's various ways of going about doing that. The simplest of all is probably to write a function. So you could write a bool function called in whatever you want, abs less fun, taking two arguments, A and B, and it just compares them, the absolute values of those arguments. And then inside the function called absolute sort, we just provide the name of the function. What's actually happening under the covers is because we've just named a function, C++ uses its address, and we instantiate std sort with a pointer to function taking two ints and returning a bool. So we are still instantiating a specific specialization of std sort, but we've thrown away the information about the specific function we're calling. We're just calling the instantiation for any function that takes two ints and returns a bool. The other problem we've got, of course, is that the function has to be defined at module scope, because you can't define functions nested inside other things in C++. You can in some languages, but not in C++. So we've had to provide an additional function at module scope. We've leaked implementation details of our function out into the global scope in this case. And we've also lost some of the benefits of the C++ standard template library because of this fact that we've just specialized the instantiation of std sort for a simple pointer to function. And I did spend some time trying different compilers, different optimization settings to see if the comparison would be inlined. And I failed to find a setting that inlined the comparison. So the function did consist in the assembler, even with high optimization levels, of some function calls to this thing that does the abs comparison. And the other problem, of course, with functions is that they're stateless. So if you have some sort of need for a stateful function object, functions are probably not going to help you very much. So a more flexible approach may well be to use a function object of some sort. So here we write a struct, which I've called abs-less. As you can tell, I'm not very good at guessing names. And we provide an operator, a function call operator, that takes two ints, and it does the same as before, returns the comparison between the absolute values. And now we pass that function object into std sort. Slight change in the syntax, because we're actually passing in an object, we have to create an object, so we need to use parens, or in more recent C++, you could use braces to generate a genuine object. Again, we've got some downsides. We've created a class at module scope. So we've still had to leak implementation details out of the function that we're writing into, in this case, the global scope. In C++ 98, you had to do that. You couldn't instantiate templates with the type that was local to your block scope. And Anthony Williams, who was speaking earlier today, resolved that in proposal N1353, attempted to resolve this by suggesting that it should be possible to instantiate templates against local classes. That is getting on for 20 years old, and it was morphed along the way, but it did eventually make it into C++ 11. One of the amusing historical difficulties that people had with this was pre-standardization, Visual Studio, I think the last one was Visual Studio 5, but don't quote me on that, used to actually allow this as part of their support for templates. And they took the support out as part of their conformance to C++ 98. So I imagine somewhere inside Microsoft, when Anthony's proposal landed, they just looked in the code history and took out the code they'd added to disallow something that used to be valid. Whereas at least one other vendor had to make significant changes to the way their template engine mangled names, because they didn't provide any name mangling for local classes. You didn't need it back in the days of C++ 98. Now, the advantage of using a type here and a function object rather than a function pointer is it's much more likely to be optimized, because there is no erasure of the type. If I instantiate, going back a page, if I instantiate absolute sort, the std sort inside absolute sort, I instantiate one where one of the template arguments will actually be abs_less. If I go back to the previous one, looking at the question in the chat, where we're using a function, although the name of the function appears, abs_less fun, what happens in the template instantiation is it just uses the type of the function. So what appears in the argument list for the template that gets instantiated is the type of begin and end, std vector int iterator, and then the type pointer to bool, well, pointer to function taking two ints, returning bool. I hope that answers the question. Now, in C++ 98 and 03, you could resolve the scope issue to a certain extent and have the abs class or struct moved within the body of the function by using a static function within a local class. So here's a possible way of rewriting it in C++03, where you're not relying upon having to have things out there in the kind of module scope. So you put struct abs as a local struct, and we have a static bool less function within that, and then that does the comparison, and then we instantiate it with the function abs under : less. But we're having to write quite a lot of scaffolding for what's basically quite a simple piece of code. And people thought there must be a better way of doing it. Some solutions were done more generically. So libraries such as Boost tried to come up with clever ways within the constraints of the syntax of C++98 of making the process less painful. So here's an example using Boost bind. One of the problems with the world back then was, which actually still continues through to C++20, is it's quite hard manipulating overload sets. And one of the problems with the example that I used was that abs, std abs, the function we're using, is an overload set, which means a naive approach here doesn't work. So we have to form a function pointer, which we do with the int star abs int equals std abs. And then we use boost bind, and we bind std less of int with two arguments, which again are other versions of boost bind, binding the abs function pointer that we've defined earlier with these magical _1 and _2, which are placeholders and will bind to the arguments provided by sort to the function. The first time you read code like this, you probably have very little idea what's going on. It does get better with practice, or maybe the pain just kind of goes away. But you may well feel that this cure is worse than the disease. If you do it a lot, it becomes easier, but it's still not very clear. There's an awful lot of scaffolding boilerplate code there visible on the screen to try and do something that conceptually is really quite simple. So to recap, I'll just have a quick check in the questions and answers. No, we're all right so far. So we've got free functions, member functions, static member functions of local classes, and some various complicated template solutions such as boost bind. And as I said at the beginning, the thing about C++ is you can still use all of these techniques. And there may be times when they're still better, simpler, clearer, more expressive, or let you do something that's harder to do with the new ways of doing things such as Lambdas. And they haven't stood still. So you can now do this, as I mentioned, with structs that are within the scope that you're in and not have to move things out to global scope. So C++11 came up with Lambdas. What we've got is a Lambda expression, which are pretty well syntactic sugar for actually writing your own local class without a name. And as I say on the slide, one of the interesting things about Anthony's proposal was that when the move came for putting Lambdas into C++11, the fact that the compilers would have to do pretty well the same work to support Anthony's local classes proposal as they would to support Lambdas meant that some of the resistance to his proposal faded away, because it was something that people were going to have to do anyway. They might as well regularize the language and support the same thing for local classes as for these compiler-written classes. So all you do is you provide, in this case, at the end of std sort, this new syntax that's emboldened, where you have this square bracket that introduces the lambda, and then the arguments the lambda is going to take, followed by a pair of braces with the code you want inside. And it's broken down kind of grammatically into three separate parts. You've got what's called the Lambda Introducer, and the mandatory part of that is the square brackets as a clue, both to you, the reader and also to the compiler that you're about to produce a Lambda. And then you have a declarator, which specifies the arguments you're wanting to pass in to the Lambda function. And then finally, you have the compound statement with the braces. Now, a couple of the decisions that were made quite early on were, first of all, you always needed a Lambda Introducer. You always needed a compound statement. And there have been moves afoot, and I'll hope to have time to cover a couple of things that people are trying to do to simplify things further. Personally speaking, I'm happy with both of those decisions, and I don't see any particular need to shrink the syntax anymore, but I know that other people do. The only part you were allowed to omit in C++11 was the declarator. If you didn't have any arguments you were passing to the Lambda, you could miss out the parentheses as well. And that generated pseudocode roughly equivalent to the previous slide. Now, if you've come across C++ Insights, you can use that to see what code the compiler visualize anyway, the code the compiler generates, and you'll find that what happens is not really quite the same as the pseudocode, but it's kind of close enough. So we have a struct, an unnameable struct, which has a function call operator inside it, and the Lambda declarator basically becomes the declarator for the function call operator, and the compound statement just drops in as the body of the function call operator. And then we instantiate an object of the unnameable type as the argument to std sort. And seeing that rewrite might make it easier to have that in the back of your mind when you're seeing code like this, to how to understand what the compiler is making of it. It's basically just turning it into code like that. Almost. A few extra little details. The first one, and most important one, is the function call operator is actually marked const implicitly. Now, this doesn't matter in this example because the struct has no data, but we'll see later on that it does. Now, while the type of the Lambda is unnameable, you can give the expression a name by assigning it to a variable. Here's the example again within Lambda absolute sort. I've gone auto abs underscore less equals, and then exactly the same Lambda as I had passed as the argument in the previous slide into std sort. Now, of course, what is the type of abs less? Well, it's a Lambda. But yes, it has a specific type, which you're not allowed to use. The compiler knows it, it makes one up. Different compilers make different choices. It's not a name that you're allowed to utter in your source code. And in fact, this is one of the very rare places in the language where you have no choice. You have to use auto to declare this data type, abs underscore less, because you've got no other name you can provide to name the variable. What you can do by naming it, there are a couple of things. The first is you've given it a name, and names are powerful. Names are hard to pick, but if you can pick a right name, you're expressing intent to the readers of your code. The compiler doesn't really care. You could just call all your variables Brenda, and no one would mind from the compiler point of view. The people that read your code would hate you, unless, of course, they're called Brenda when they might like you. But by calling it abs less, you don't need to read necessarily the body of the Lambda to get an idea of the intent. The second thing you can do by using a variable is I could use the same Lambda elsewhere. I don't have to duplicate the code. I can just use the same name Lambda. And there's two benefits for that. One is that I'm not repeating myself by writing the code twice. And the second is I'm instantiating one object. I'm cutting down the amount of separate instantiations the compiler needs to do. Because if I write the same Lambda using the same symbols and assign it to a different variable, I'm actually generating a completely unrelated class. So I'm going to get some code bloat in my object modules. You can, of course, generate lambdas at other places than at block scope. So I could have a lambda that sits out there at a module scope, perhaps as an implementation detail for my class. One of the problems with lambdas that I don't know of an agreed solution is how on earth do you format these things? And different people have got different ways of doing it. Your mileage may vary. The place I'm currently contracting, we've got it very simple. We've just got a Clang format add-in that just formats it. We've stopped having any arguments about formatting. The way Clang format is set up to do it just works. If we don't like it, that's just tough. You could perhaps argue to change it, but it saves an awful lot of headaches about thinking about the right way of formatting it. All of these ways I've seen and more. It's quite good if you can come up with a convention in your code base to make it clearer so that you don't have to kind of waste cycles in your brain decoding the syntax. You've probably got enough problems decoding the meaning. One of the little things that was added in with lambdas was there's an implicit decay to a simple function or function pointer, which is useful in times when you're interacting with code that expects to take function pointers. So here's a simple example of in some header I've included, there's a type called callback, which is a function takes an int, turns a void, and I've got a set callback function method or something that takes a pointer to one of these. And I can use that in my C++ code by passing in a lambda. What happens is that the compiler generates, as before, the usual anonymous struct with a function call operator that takes the argument int val. There are no functions here. There's just member functions. And then the compiler generates a func. It makes up a function that just instantiates the object and calls the member function on it. It does that for you under the covers, and this is known as lambda decay. So what effectively you're ending up with, though, is you're doing much the same as this example, where I've pulled it out into a named function pointer. And as we saw before, the disadvantage with doing that, if you're using it as a function pointer to a template, is you're forcing the compiler to instantiate the template against the type of just pointed to function, rather than the specific type of the lambda. So it's not a good technique to use in a template world. It's typically used just where you've got some externally provided API that takes function pointers. The next thing you can do with lambdas is you can actually capture local variables that are in scope. So again, this is a Mickey Mouse example. It doesn't have any great sort of real meaning, but it demonstrates the case. I've got a struct inside which I've got a method that takes a value as an argument, and I write a lambda that wants to compare the test that's provided as the argument to the lambda against the value that was passed in as the argument to the overall function. What I do is I name the variable I want to capture inside the Lambda Introducer. So all the examples I've shown so far, the Lambda Introducer is just a pair of square brackets, but within it, you can put quite a lot of stuff. And in this case, I've just named a variable. So it all works nicely. You, the reader, see one value. You see a value being provided as an argument, you see a value being captured, and you see the same value being used. Under the covers, though, the compiler's done something else. What effectively, you can do the same thing with members fields within the struct. Whoops, apologies. So the other thing you've got access to within a member function of a struct or class is fields within that. You can't name the field directly. What you have to do, at least you couldn't, what you have to do is to name this. And once you've mentioned this in the capture list, you can now use things that this refers to, such as field. So again, I've got an example here where we've used field and value inside the body of the Lambda, and field is referring to a part of member data of the instantiating object, and value is referring to something we provided when we called it. Of course, C++, we've got call by value, call by reference. And there's a choice when you capture variables. Do I want to capture a copy at the time when the Lambda was created, or do I want to copy a reference to the value that was passed in that will track any changes to it? If you want to form a reference, you put an ampersand. So the default is by value, which I think makes sense because C++ generally is value-based. And then the non-default case is you put an ampersand. Now, in this example here, we've captured one argument by value, and one argument by reference. And so although they're used the same way within the body of the Lambda, they're going to behave slightly differently. At the point where we create the Lambda, we copy value and we form a reference to reference. So if we then change value and reference further down before we invoke the Lambda, what we end up with is we print out value. That's not changed. That's a local field of the Lambda. And we print out reference. Well, that's not changed. It's a local field of the Lambda, but it's a reference. And of course, the thing it refers to has changed. So this will print out 10,11 when called with 10,10. I've just spotted some questions picking up. Let me just have a quick look. Does the compiler name the local struct? No, we name the Lambda, but the variable type, but we never name the actual Lambda struct. And yes, struct or class, it didn't really matter very much. I'll show that a bit more going on. And never have enough real estate on your screen. I'm afraid I don't quite understand the last question about can't we just call the Lambda using Lambda call operator. You could maybe expand that further. I'll try and get back to it. Okay, let's go back to presentation and expand it slightly. So in this one, I've expanded it out, and yes, it now makes a difference. So I've made it a class, __ anon, because we've now got some member data in it. We've got value and reference. And for kind of exposition purposes, I've just put __ in front of all the things that are compiler magic. The value and reference are private. You're not able to change them. So although you could form an expression that referred to them by, effectively dereferencing the Lambda, it would be ill-formed because the reference would be to something that's private. And then we have effectively a public constructor. I'm hand-waving slightly here, as anybody who's looked inside it would actually know. But effectively, you've got a public constructor that takes a value and a value by reference. And then I've got the operator, function call operator, const, which prints out __ value and __ reference. And then when I set up the Lambda variable, I'm creating an instance of anon and passing into the constructor the value and the reference at the point where the Lambda variable is created. Of course, as soon as you start capturing by reference, you have to think about lifetimes and how long does the captured object stay around. It's sadly, as is often the case with dangling references, surprisingly easy to break things. So for example, here I've got a make adder, and I pass in a value that I want to add to the number I add passed to the Lambda. And I'm returning a Lambda. You can do that, it's fine. I have to use auto because of course I can't name the type, but I can return a Lambda. And I've accidentally captured by reference. the value passed in. And then all the Lambda does is return n, the argument to the Lambda plus value. So in my main, I attempt to call makeAdder with 10. This passes 10 in as the argument. Value has the value 10. It captures a reference to this value inside the body of the Lambda. It returns it. I've now got add 10 that holds a reference to what was the argument provided to makeAdder. But now it's just bytes on the stack. Who knows what they hold? I then invoke the Lambda by passing in 9, and I'm hoping to get 19 out. But when I tried it on a couple of compilers, I got 18 on one of them. I got minus 13,319 on another. When I tried it again, I got a different value because I've just got a dangling reference. It's pointing to just bytes on the stack. You could even end up with various other things going on. If you're running with some sort of undefined behavior sanitizer, your program might just terminate. And additionally, there are things that aren't captures. So inside the body of your Lambda, you can refer perfectly happily to block scope, global, static variables, etc., static members of the containing class without needing to capture them. They're just visible because of the scope rules of C++. So here's an example just to demonstrate that, where inside the body of the Lambda, towards the bottom of the slide, I am referring to a global, a block static, and a class static. And in fact, if you try to capture any of those, you'll get a compiler error because you're not allowed to capture these sorts of entities. One of the other things that was added into C++ 11 when Lambdas were added was the ability to have a default capture mode. The verdict is still open as to whether this was a great move or insanity. And some people like them, some people don't. Some people work in environments where they're banned, but they are part of the syntax. What it lets you do is to implicitly capture variables. And you've got two options, equals for copy and ampersand for reference. This is a case where it's slightly asymmetric. When we have named capture, you put nothing there for a copy and ampersand for reference. But we need a way of disambiguating between open square bracket, close square bracket, which has no captures at all, and open square bracket and something that indicated you wanted default capture to be copied. And then if you want something to be captured that's not using the current default, you can specify it explicitly. So here is our example where we captured value by copy and reference by reference, written slightly differently. I just use equal, and we don't need to name the variable value. It will be captured by copy. The problem is, as is often the case, anything that's done implicitly may not be what you intended. This code might be correct now, but later on, we put another name inside the body of the Lambda, and we capture by copy, and we might have, when writing the code, have been thinking we were capturing by reference, and not even noted that we were inside the body of a Lambda rather than inside the body of the method. It's also quite complicated when it comes to implicit capture of fields within the class you're in. Here I've got a nice simple example inside that same struct type I had before, where I've captured implicitly by copy. And I've got the same line of code I had before, field less than value, but actually field is captured by reference and value is captured by copy. And you think, how? Why? What? They're both captured by copy, surely. The problem is field is accessed because this is captured. And although this is captured, it's a pointer. So we just have another pointer set to the same object that this was originally, which means with dereferencing this to access field, we're referring to the same field. We've got a reference effectively to field. And in fact, as you can see in the note at the bottom, capturing this implicitly is deprecated in C++ 20 because it can cause so many bugs. So here's the pseudo code again for that Lambda capture to hopefully make it a little bit clearer what's going on. We've got our class again. I've used double underscore for the hidden things. We've got a class anon. It holds a pointer to the outside class type star double underscore this, and it holds an int value. And in the function call operator, we return double underscore this arrow field less than underscore underscore value. The next thing you might want to do within a Lambda is to modify some of the captured variables. So here I've got an example where I've got a Lambda that wants just to provide a simple counting functionality. So I set up a counter of 0. I capture it by copy in the introducer for the Lambda, and I then want to increment the counter. Every time I call the Lambda, I increment the counter. I need to add this keyword mutable at the end of the Lambda declarator to tell the compiler that I want it to create a function call operator that's not const. This is one of the cases where we were able to get things right in C++11. The default for Lambdas is they're const. The default for other functions is that they're not const, and you have to add the const keyword. For Lambdas, we've got it the preferred way round. So now if I invoke the Lambda, which has got capitalized for reasons I don't understand, we invoke the Lambda, it will output 1 the first time, 2 the second time. But if I look at the value of the counter, the local variable in scope, that hasn't changed because we were inside the Lambda capturing a copy of counter. Warning though, just like in regular classes and functions, etc., const is shallow. So if you've captured a variable by reference, you can modify it even without the mutable keyword. So if I capture counter by reference in this case, and I haven't put the mutable keyword on, although I can't change any of the fields within the Lambda in the body of the Lambda, I can change counter because I'm changing the thing that the reference is referring to. And lastly, just a question about the cheating the anonymity. I can't name the type, but can I? And the answer is you can actually use the name of the type in certain cases. So here's again a simple example of a Lambda. I can do things like ask the compiler to tell me what the size of the Lambda is. I can get the type ID of the Lambda. I can call .name on that. And I can print out what the anonymous name is that compiler has generated. It's not much use to me, apart from just I'm curious about how compilers do things, but there are things you can do with the type ID. I can even declare another variable, decal type Lambda. So I've now created another Lambda, L2. However, there's not much I can do with it apart from create a copy of the existing Lambda, because the constructors you'd need to generate a different Lambda or to have a different capture variable are just not available to you. Now, if you think about it, one of the reasons why we want Lambdas to be copyable and movable is that we want to be able to pass Lambdas into standard algorithms. And when you pass a Lambda into an algorithm, the algorithm in turn may pass the algorithm argument further on, and it may need to make copies of the provided argument. So Lambdas needed to be copyable and movable to be usable in as many places as possible. Right, quick recap here and a reminder for me to check the questions. Is there any advantage of using a Lambda inside a class versus a function? Again, I'm not quite sure what the question's trying to ask. I've answered that one. Haven't read any more on that one. Any performance difference between passing by value or reference in the Lambda? Yes, there may well be. I'm going to do a little bit more about that later on. I hope to answer your question, but if I don't, it's much the same as in general if you're passing value or reference. In the cases where they're cheap to copy, it doesn't matter. So my examples I've all used int, and that was partly deliberate so I could duck this question. If things get inlined, then again, the compiler may well be able to eliminate some of the copies or to eliminate the work done by some of the copies. If we're doing things by reference, the compiler may well have to continually reload because it may not be able to prove that the value is not modified. So aliasing rules mean you may get multiple accesses. Also, the accesses typically are indirect. So hopefully that was enough of an answer. With implicit capture, does the anonymous class contain only the set of variables used in the body? Yes. In fact, one of the things that is a problem that I will briefly mention, if time permits at the end, is that the set of things that gets captured is obviously picked at the point when the compiler syntactically analyzes the body of the Lambda to see what you use, and it assembles a list of the fields you use. Even if later on the optimizer manages to eliminate some of those, they're still part of the Lambda. And so the Lambda can't get any smaller because you might, for example, have used size of against it. So it can't change the internal structure. But it doesn't capture everything, even with an implicit. It only captures the things you actually use within the body of the Lambda. There's no performance cost. The implicit versus explicit capture is purely to save you typing. And we can call a Lambda directly where we declare it. Yeah, you can just put the parentheses at the end of the Lambda. So you can, I'll have an example of that coming up in just a minute. So we've got a quick look at the syntax for Lambdas, which removes some of the scaffolding, but I find it helpful to think about it in terms of what the compiler is writing under the covers to make it clear what's going on. And the Lambda behaves very like an anonymous local class. We've got this choice you need to think about with variables, whether you're capturing by value or by reference, and you will sometimes need to make your Lambdas mutable. C++ 14 added generic Lambdas. So you could make the type of the arguments passed to Lambda just using at that point the word auto. And the compiler would work out, deduce the type from the use of the Lambda. So here, for example, I've taken the earlier example from the that I did in the C++ 11 case, and I've changed the type from int to auto. I've now removed the specification that I provided of the type of A and B. So I can use this now in, as I've done here, in a template, and the compiler will automatically deduce the type of A and B. Now, in this case, of course, I could work out what the type of A and B is. It's going to be one of these dependent types from stud vector, but it doesn't really buy me much to do that. And I can just use auto and have a Lambda that melds itself to the type that it's called with. So these are very useful. They're sometimes called generic, sometimes called polymorphic. The other thing you can do with this is you can invoke the same Lambda. I can save the Lambda as a variable. Here I've got auto increment, and I can invoke it with different types. So I can increment int, and I can increment a double star. And obviously it'll be doing different things. It's going to be doing the same logical operation, plus plus v, but on two different types. One of the things this meant was in C++ 14 and 17, of course, you could create a Lambda with deduced argument types very easily, but you couldn't do the same thing with a regular function. So it wasn't possible until C++ 20 to write increment as a regular function, void increment auto ref, for example, v. I'd have to have written that using the template type name T syntax. But support for using auto like this for regular functions was added in C++ 20. So the previous example I had is Syntactic Sugar for this. We've got as we've seen many times before, our anonymous inner class and our function call operator. I've missed out some of the boilerplate here, including the public, but it's implied. And the thing about our function call operator here is it's now become a template type name T, void, operator, parens, and then tref v. So the compiler has written a member function template of the anonymous inner class. This is a case where templates get special rules. You can't write that. You're not allowed templated members of block scope classes. So it's one of the very, very few places where Lambda is not just syntactic sugar. It's actually able to do something that you, as a user of the language, are not. And of course, there are a couple of papers out there to try and fix that. In fact, I think they both arrived in the same mailing, P1988, allow templates in local classes, and P2044, member templates for local classes. They've now been combined into a single merge proposal, 2044. I hope it makes it, although actually it's more complicated than you might think to allow member templates in local classes. The case for a Lambda is actually quite constrained because of the syntax of a Lambda. If we allow member templates generally in local classes, there are quite a few issues that need to be thought through. But I'm still hopeful. I think it would be a good step forward to allow that. The other thing that was added was sometimes it's useful to be able to initialize the capture variable yourself from an expression. So I gave an example a few slides back of a Lambda with mutable on the end that incremented a counter that started at 0. And I had to, in that example, create a local variable called counter and then capture it, which really is a bit silly. So here I've created a capture with an equals. And that tells the compiler I want to actually have a local member of my anonymous class called counter with an initialized from 0. And the compiler uses the type of the expression on the right-hand side to work out the type of counter. And I can then simplify in some cases. The other thing, of course, I can do is I can rename the capture variable. So here I've got a case where there's some value I've got inside the body of the function I'm in, and I want to use that as the initial value of my counter. But I don't want to keep the name value because I'm using it in a different way. I want to express the different use I'm giving it by changing its name to express intent. So I can assign value to counter. And this syntax also allows you to explicitly capture a single field from the containing class, which, as I said before, you couldn't do previously. I can name the field in the initializer of the captured variable. So here I'm using slightly different syntax just to show you the other way of doing it. You can just initialize it with braces. So I've initialized field from field. This can look a bit strange the first time round. It's very, very similar, in fact, syntactically to a constructor initializer list, where it's relatively common to name the arguments of the constructor the same as the name of the fields, and just initialize each field from the same named argument provided to the constructor call. And we're doing much the same here in this case with the Lambda. We've initialized the captured variable field from the member of the class field. It also gives you the option of moving things rather than just copying things. So I can have the expression being a std move. Additionally, you can capture a copy of *this, not just this. What that does is it adds a copy of the current object. Now, if you're in a deep class hierarchy, *this will be the compile time type of the object, not the runtime type. So I'll get a variable that is a slice at the current level in the hierarchy of the current object. And this can be useful in quite a few cases. One particular case is where I'm passing the Lambda on to something else that's going to hang on to it, and the Lambda will outlive potentially the current object. So from the proposal paper itself, I took this example where to do this safely in C++14, you could use init capture. You create a local variable called temp that's initialized with *this. And now I return temp.value, and temp is a named capture inside the Lambda that is initialized with *this. And in C++17 and beyond, you can just name *this, and now you can just name the field value, and it will automatically use the value that's in the copy of the object that you were in when you invoke the Lambda. Just a quick check of the questions. I've answered that one, I believe, about the anonymous class. Is there a case for capturing by const ref? Yes, in just the same way as in any other case where you've got a reference, you may want a mutable reference, you may want a const reference. It's entirely up to you. There's a question about at what point should you say a Lambda would turn into a normal member or member function. I hope to talk about that a little bit, but it's a good question about Lambdas. Where do you stop using a Lambda and use something a little bigger? As I said, I hope to cover that shortly. If you have a generic Lambda called twice, it's a single class with 2 overloads. Yep. And this does make a difference if you're using the local variables within the body of the class. So it's the function call operator that's been overloaded in a generic Lambda. I think that's all the open questions. I apologize again if I haven't answered them all. One of the use cases for Lambdas is delayed initialization. I first came across this as an example from Herb Sutter, but I'm sure other people have come across it too. You have some code that has slightly complicated initialization. So here, for example, I've got a double delta, and I'm running this particular algorithm in various modes. If I'm in high precision mode, I set some very low value for H1. I do some complex calculation involving H1 and potentially other arguments to the function. And then somewhere inside the that if case, I assign something to delta. Else, I have another condition and I assign to delta. Otherwise, I have a fallback of just a hard-coded 1e minus 6. And as a reader of the code, there's a couple of questions. The first is, does delta change? It's not const. Could it change further on? If I read on 3 pages of code and I see a reference to delta, has it got the same value it had at the beginning? And the second is, have I always initialized delta? I might have forgotten. Now, it's possible in the right compiler mode, you get a warning if the compiler is able to analyze the code properly and detect that double delta is never initialized. But of course, if delta does have it's of a type with the default constructor, you've default constructed it and you never change it in your initialization code, and maybe you meant to. Maybe the fact it's got a default constructor was just an accident. So you can rewrite that using a Lambda. So I now make the delta const because I'm initializing it at the point of declaration, but I initialize it from a Lambda. And I take everything implicitly by reference because effectively I'm just wanting to drop this code in line into this point in the function. And it takes no arguments because I'm going to invoke it at the very end of its use definition. The Lambda starts with the open brace. The code is the code that was there before to initialize, except all the assignments are now replaced with a return statement. And the Lambda is returning in all 3 branches. And then at the end of the initialization, I just invoke this Lambda. Now, again, the first time you see this, you probably need to go and lie down for a bit if you've not seen it before, because we've got parentheses in 2 places. We've got square brackets with ampersands inside. The syntax is a little complicated, but you do get used to it. And the benefits are, and why it's worth the pain, is that delta is now const, and you know it can't change later on in the function. And also, you're far more likely to get a compiler warning if you have a lambda that doesn't return, because functions that fall off the end of the function is a much more detectable and concerning problem than variables that aren't initialized. So if you accidentally omitted the return 1e minus 8 from the middle case here, for example, you're going to get a compiler warning that you haven't initialized the value. Lambdas are also useful, or can be useful, as a refactoring tool. Very often when looking at particularly old code, you're working your way through quite a large method and you identify a block of code that appears twice, or maybe only once, but it does form a logical function. And now one way of refactoring that would be to pull it out using extract method. But an alternative in C++ is to use a lambda as a local alternative. And you've got some idea of what you think this block of code does, which is what you would have used as the name of the method. Well, just generate a local variable that's a lambda using that name and put the body of this code as the body of the lambda. Similarly, you may find that that similar block of code is repeated a couple of times within the body of the same function, in which case you may be able to use that by turning it into a lambda which is used repeatedly and reduce the code duplication. The body of the lambda is the commonality, and you've named it by extracting it out as a lambda, and then the arguments that are supplied to the lambda specify what's different in the two cases or multiple cases of this block of code. In C++20, we added in extra stuff into Lambda. You can provide template arguments. In previous versions of C++, as I mentioned, there was this asymmetry between lambdas and regular functions. We could have a lambda that took auto as the type, and the compiler would automatically generate a generic lambda. Or we could have a function call operator within a struct that was templatized on type name t. But two syntaxes were very different, even though the usage was very, very similar. And as part of including concepts in C++20, you can now use auto in the regular function call operator syntax. So you can now write, for example, struct auto ref, and then auto x, and have that work in much the same way as in a generic lambda. And conversely, again, for symmetry reasons, you can now use type name in the lambda syntax. So rather than using the syntax with auto x, I've actually named the argument as type name t and provided t as the argument type. And the main reason for doing that is there are advantages in certain cases of actually having that name t available. In this particular case, obviously, it doesn't really add any particular benefit. But if you have two arguments, for example, I could now name them using the same type name t, and that guarantees that they're the same type. If you want to express other constraints on the type, that becomes easier once you've named it. If you want to express what the return type is, for example, you could instantiate an object within here, within the body of the lambda, using the named type t. The other thing you can do in C++20 is you can constrain the arguments in just the same way as a regular function could be constrained. So if I've got a constraint called numeric, for example, that lets me restrict things to types that are loosely numeric, whatever that means in my particular domain, I can constrain it by putting numeric in front of the auto in a regular sort of generic lambda. I could also constrain it using the syntax where I go numeric t as the argument to the template syntax. Or I could add a requires clause at the end of the type name t syntax. And that is quite useful where I want to express a requirement that uses multiple of the types that are provided as arguments to the lambda. So it's all got a bit more complicated, but the additional flexibility is very useful in some cases. So to recap so far, we've looked at generic lambdas, where you just use the word auto for the type of the argument. We've looked at init capture, where you can capture variables using an expression, and you just name what that expression is, and it then becomes a field inside the Lambda. Or you can capture, for example, a field of the containing type by just capturing its name and assigning it to a local variable within the body of the Lambda. I've done a couple of use cases and talked a little bit about how Lambda and template arguments and concepts have got harmonized. So I think the language in C++20 is a lot more sort of symmetric, and tricks and techniques that work with member templates, etc., can be used with Lambdas and vice versa. One question people often ask about Lambdas is, what does the performance look like? And actually, I was struck by Chandler Caruth's CPPCon presentation a couple of years back with the provocative title, "There are no zero-cost abstractions." And I think that's generally a good thing to think about. Whenever you use an abstraction, I forget who it was, somebody described it as selective forgetting. You are throwing something away. The benefit, hopefully, is you have a higher level of understanding, a higher level of generalization, but there will be, potentially anyway, some costs. Whether the costs matter depend upon what they are and what your constraints are. So Lambdas look simple in the syntax. There's a reasonable amount of supporting machinery being written by the compiler. So the compiler's having to write more code than you originally provided. I've not come across anything indicating that this significantly impacts compilation time. It's not particularly difficult code for the compiler to write. It doesn't seem to be very expensive. The cost of syntactically analyzing the Lambda expression doesn't seem to be very high. One thing to bear in mind, though, is you may get code bloat, where you get multiple instantiations of similar looking Lambda expressions. They are each a separate instantiation of a completely separate type. And in particular, when you do this in a template world, Lambdas are classes, and the name of the Lambda will include any template arguments of any surrounding entity. So here I've got a simple example of a function that takes 3 template arguments, t, u, and v, and somewhere in the body of the method, I invoke a Lambda that just takes a single argument of type t, and the body of the Lambda just does stuff with t. I've not used the template argument types u and v, but every single instantiation of this Lambda will include the fact that it's part of a class inside of f that's instantiated on t, u, and v. So you'll get a separate instantiation for every distinct f. And what you can do to resolve this, if it becomes a problem, is using the same technique popularized by scary iterators. C++ specializes in really, really bad acronyms. SFIN-A is one, scary is another. What it basically means is you refactor to pull the stuff that depends on just one of the types of a template out to a higher level where it only depends upon the type you're using. So in this case, what we could do is we could pull our template out as a const extra auto Lambda, and it's just depending upon a single type now, the type of T, and then I could use this inside the body of F. And this hoisting technique obviously has a slight downside in that it's now exposed to slightly more from a scope point of view, but it does cut down the bloat. And if you find that you've got a lot of separate instantiations of effectively the same template, this is one of the things you can do to reduce that. But I suspect actually most of you wanted me to go straight on to not so much the compile time cost, but what the runtime cost was of Lambdas, and does the resultant generated code run slower? Well, one hint to all this is you can add const extra to a Lambda. And in fact, if you don't, and it satisfies the constraints of being const extra, it will be marked as const extra implicitly anyway. What const extra means is the compiler must be able to evaluate it at compile time. So it must be able to completely deconstruct the body of the Lambda and work out what it means, so to speak, at compile time. As a little note, you can also mark a Lambda as const eval in C++20, so it can only be evaluated in an immediate context, which means you're never going to get the back end seeing the body of your Lambda. So here's a simple example where I've used a const for Lambda just to give you an example. I've got a function void, which is templatized on a non-type template parameter dims, and I've got a Lambda called square that just returns the square of its argument, and I use that later on in the algorithm to instantiate an array of doubles of size square of dimensions. So I want to make sure that it's const expra so that it's valid syntax, so I can mark square as const expra. Now, when you use lambdas in an unoptimized build, you'd expect that the boilerplate the compiler's written, the anonymous class and the function call operator would be there. And it's not a great deal of a concern to most people. And in most of the cases, certainly simple cases, if you turn on just one level of optimization, then the compiler will typically inline the whole of the Lambda class and the calls to its operator. So I thought I'd test that with a simple example. We've got a raw func that just returns val times val, and we've got a Lambda func where we generate a Lambda that squares the captured value of val, and we set the return from that Lambda invocation to ret, and we return ret. So we've made something that was 4 symbols into considerably more. We've used lambdas. It's all quite complicated. In an unoptimized build on x86, 64, raw func is 4 instructions or 7, depending on which compiler. They're not identical instructions, so it's not like MSVCs being much better. It just made different decisions about which instructions to use, and the calling conventions in the 2 cases were different. The Lambda func was 11 instructions in MSVC or 13 with GCC and Clang, but it includes method calls. In MSVC, it includes 2, one to the constructor and one to the function call operator. In GCC and Clang, it includes 1, the function call operator, and those methods in turn total to either 14 instructions in MSVC's case or 10 in GCC and Clang. So we're comparing 4 instructions in a debug build of MSVC to 25 instructions, 2 of which are calls, so that's pretty bad, or 7 instructions in the GCC Clang case with 23 instructions, 1 of which is a call. So that also is pretty bad. But as soon as you flick on 01, minimal optimization, the code generated for raw func and lambda func is identical. Both are 3 instructions on all 3 compilers. So just to go back to look at the code again, on the left, we've got a very simple expression used as a return. On the right, we've got a lambda, an assignment, quite a lot going on, but in both cases, just 01 is enough to completely inline and eliminate the whole of the lambda. In less trivial source code, if performance really matters, then the only thing you can do is measure. Is it fast enough? If yes, I don't care. If not, look at the output. Tools like Godbolt let you look at the output and confirm whether or not the lambda has been optimized away. As you build up more complicated code, particularly where lambdas are passed as arguments into functions that in turn pass them as arguments to different expressions, you'll eventually hit the limit of how far the optimizer is prepared to go, how much resource it's prepared to expend on optimizing the calls to your lambda. But you may be surprised how far you can get. It's been a very key area of research by compiler writers. People have used lambdas a lot ever since they've arrived in the language, and people have worked very hard to reduce the runtime cost of lambdas and the optimization opportunities for lambdas. However, if the lambda isn't totally erased, as I briefly hinted at earlier in my mention, one thing to bear in mind is that the implicit class layout of the lambda is picked very early on in compilation, and you can't change it during optimization. This also, of course, means if you've captured lots of variables, you don't know where they're going to be in memory if you're desperately worried about cache hits. It's not quite clear to me whether this is a significant problem, or if so, how often. And as is normally the advice for performance, get the code working correctly and solidly first, and then measure and see where you need to spend your time on performance. Some of the things I mentioned earlier about the syntax, people have been chipping away at the syntax, trying to slightly simplify it. One of the things that was a slight bugbear was, I mentioned you could omit the parentheses in the case where there were no arguments being provided to the Lambda. Unfortunately, mostly by accident, it turned out that the phrasing of this meant you had to use mutable. If you wanted to use mutable, you had to use the parentheses. So here I've got a case of a very simple counter called sec. I want to do one of these init captures of val from the value 0, and then just keep pre-incrementing val. So it needs to be mutable, so I can change val. I don't pass any arguments to the Lambda, but I used to have to provide the parentheses. P1102 R2 was approved last month in the virtual plenary meeting that we held, and will be fixed in C++ 23, barring accidents. If something happens, you have to take it out again. But you'll be able to now write auto-seek equals square bracket val equals naught, mutable, and just return plus plus val. This may or may not be desperately significant. Some people actually have a coding convention that you are not allowed to omit the parentheses because they think the ambiguity in the reader's eye, even if the compiler knows what it's doing, it's clearer as a signal to the reader that what you've got is a Lambda. And there are some possible directions for future shortening. Lambdas in C++ do use more syntax than some languages do. The disagreement is how much of it is necessary. Some of it is because we've got both value and reference semantics and const, and we need to have ways to put that. Some of it is caused by substitution failure is not an error, SFINE, and there are some constraints that imposes on what is or is not possible with the syntax of Lambdas. Some of it is because the parsing of C++ is quite difficult, and there are some restrictions caused by the syntax itself. But there are still attempts out there to allow abbreviated syntax. In particular, some people would like to be able to remove the scaffolding of the function call, the braces and the return statement, and just to provide an expression. So there was a paper a couple of years back, 3 years ago, I think, that proposed a syntax of kind of an arrow-like symbol and expression. Now, that paper itself was rejected in discussion at EWG, but they polled separately and passed that they are interested in the principle of exploring shorter syntax in the future, but just not that particular paper. So we may end up with a simpler syntax. So I'll just, before I finally conclude, just a quick check down the questions. What point should you say a Lambda should turn into a normal member function? I haven't really covered that. I didn't get that one. I think I've answered that one. I think I've answered that one. Yeah, I think they're all answered. Again, apologies if I've missed one, apart from Hemi's question, which I may cover if there's time in the questions. So to conclude, Lambda is a very, very useful part of C++. Principally, they're syntactic sugar, but there's nothing wrong with that. There are a couple of things you can do with Lambdas that you can't do with your own code. Think hard about the capture, whether it's by value or by reference. You need to consider the lifetime if you're going to capture by reference. If you're capturing by value, bear in mind that your Lambda may be copied, so you may have additional costs of copying the Lambda capture. I recommend preferring to avoid implicit capture. I think it's quite useful in the Lambda to spell out explicitly the things you're using in the body of the Lambda to avoid surprises. And I do also recommend very often using a named variable for the Lambda expression can make the code more readable. When you have lambdas, particularly multiple lambdas, within the body of a function call, it can get quite difficult for the reader to work out what's going on, and also to understand the intent of what the lambdas are doing. And by using a named variable, you can make it clearer for the reader. It ends up generating pretty well the same code for the compiler, but it makes the job of the reader easier. Looking at the advantage of using a lambda inside a class versus a function, one of the things that's interesting about most languages is there's multiple ways of doing things. And one of the questions about C++ is, when is the right time to use a lambda inside a class rather than to use a free function, a member function? And I think, as Kevin would probably say, it depends. One of the thoughts on my part is, if it's a single use, the use case is very specific, it's only required for the implementation of a specific member function, there's no particular benefit in making it available elsewhere, because you then end up with a problem that you might want to change it in the future and you have to check to see where else it's used. You've added to the kind of cognitive overhead of understanding either the header file, which has got extra functions in, or the member functions of a class. You've added more member functions. So having a lambda within the body of the class itself, or within the body of the method, is probably the right way to go. However, if a lambda gets more complicated or has useful functionality that you might want to use elsewhere, extracting it out as a member function or even as a template function might well be the right way to go. If lambdas get too long, I think that's normally a bit of a code smell. It's an indication that there's probably a larger concept in there that might be better supported by writing a class that actually encapsulates the concept. Lambdas are quite restrictive in that you've only got a single function call operator. It might make more sense to have a class with a couple of methods. You might want to have a setup and then to call some calculate method multiple times. And you can do that sort of stuff with a lambda, but it does make it more complicated and harder to read. So hopefully I've given at least some answer to that one. Any other use cases, apart from algorithms and real life use cases where functions can't be used? You can always use a function, although you have to think about the capturing. If you are writing a lambda in the context of a scope, it's very, very easy, and the syntax helps you to capture copies or references of local variables or arguments. If I write a freestanding function, I either have to pass those in as arguments or make it a member function of a class which gets initialized. So there's more boilerplate I need to write to have something that's outside the scope of the block I'm in, rather than a lambda. I've answered the lambda call operator. I think I've answered that one. Okay. I think that's about all the questions. If anyone has answered a question that I haven't answered properly, please feel free to, probably at this point, put it in the chat, because the list of open questions is getting quite long.
Roger, there is one more.
There's one more, yep.
Yeah, just coming from Mike. Well, Mike asks, can a lambda with captures be passed as a function pointer? And then he puts in brackets, I'd thought not.
I'm not seeing it. I don't know why I'm not seeing it. It's appeared now. That's a bit of a delay. Interesting. No, I should have said that. Thank you. Good question. Can a lambda with captures be passed as a function pointer? And the answer is no. And the reason being is what happens under the covers is when you have the function pointer, the compiler is writing a free function. And the free function creates default constructs effectively the anonymous class and then invokes the function call operator. And so we don't have in this free function, we don't have the arguments to pass to the constructor for the Lambda class. So we can't treat it as a function pointer. So I hope that makes that clear. That's a good point. Well, I think that looks like all of them. Thank you for your attendance. I apologize for my laptop and its microphone issues. I hope it wasn't too disturbing for you all. And I hope you didn't miss much in the bits where the microphone was pretending to be a space creature. I will hang out in the back in Remo. I will attempt to sit on level 4, because that's probably the quietest level if anyone wants to join me. And I look forward to seeing you in person in due course.